Well, welcome everyone, and thank you for joining us first thing in your morning. We'll just get started right away here. It looks like we have everyone logged in. For those who didn't join us for the last couple of sessions, my name is Jenna Annett, and I work with the Community Energy Association, or CEA. I'd just like to introduce you quickly to CEA and the Kootenay Clean Energy Transition Project. So CEA is a BC-based nonprofit. We've been working for over 25 years with local government and Indigenous communities across the province to reduce emissions, conserve energy, and help progress us to a low carbon and healthy future. Next slide, please, Rob. So KCET, or the Kootenay Clean Energy Transition, is a project that was developed to address shifts happening in the energy efficiency, renewable energy, and home comfort space. So through KCET, we want to help Kootenay and boundary communities prepare for a more energy efficient and healthy future through training in the building industry, community workshops to help increase knowledge and awareness, and pilot projects that we can test and scale up. So thanks to the generous support of the organizations you see listed at the bottom of the slide, we're offering this free webinar series as a part of that training and capacity building piece. Next slide, please, Rob. Perfect. So I'd like to begin our session today by acknowledging the Indigenous peoples from all of the diverse and beautiful places we are joining from. So the land on which I'm currently joining you from is now known as Nunavut, but for thousands of years was occupied by Indigenous populations and is the traditional territories of the Snakes Nation, the Silks Nation, and the Tanaha Nation, and is home to the Métis and many diverse Indigenous persons. So I'd just like to acknowledge with gratitude and respect that the joy I am privileged to experience daily in these mountains and waters is in thanks to their generations of stewardship. And the next slide there, please, Rob. Perfect. So with so many of us on the call, I'd just like to take a minute right away to quickly talk about some housekeeping items. So if you have any questions as we go through, we really encourage you to just raise your hand and Rob will get to your question right away. Alternatively, you can put your question in the chat and we can save it for the end of the session when we have time for a facilitated discussion. As you would have noticed when you logged on, we're recording this webinar and we'll be sharing the recording along with the slides with everyone here via email within the week. And it will also be posted on our website at www.shiftshappening.ca. For those of you collecting CPD points, a confirmation email of your attendance will be sent out later today. So those are all of our housekeeping items. So it's with great pleasure that I introduce again Rob Pope. He's a senior consultant with Ecolighten Energy Solutions. Rob has vast knowledge and experience in the HVAC industry, and he's been involved with installing and servicing energy efficient systems since day one. So a huge thank you to Rob for joining us again today and sharing your wealth of knowledge. And with that, I will pass it along to you.
Thanks, Jenna. Before we get started, I'm just wondering if we could ask everybody how many people know what a balance point is. I think raising your hand or putting it in the chat would be fine. We'll check in on that number as we go. Importance of balance points. I can't emphasize enough how important it is. And hopefully by the end of this, you'll understand why I say that. Today, we're going to talk about what the balance point actually is and why it's important, but we'll also talk about how to find a balance point and how to use the balance point to select equipment and systems. And we'll do a walkthrough of an actual calculation for an actual project. And we'll finish that hopefully in time with enough time left over for questions and answers. So yeah, let's get started. First of all, there's two types of balance points, and it's important to distinguish them from each other. One is the thermal balance point, and that is the temperature, the outdoor temperature at which the heat pump, which is the primary heat source, is no longer capable of meeting the indoor set point conditions. In other words, it runs out of the capacity to do the job. The other balance point that's often talked about, but it's very much more complicated, is the economic balance point. And it includes the capacity part. In other words, when the system is no longer able to meet the load demand, but it's also a measure of when it's not economically feasible to continue to use the heat pump as the primary heat source. In other words, you might have a backup system with gas or electric, and that might take over. So one is about capacity, one is about efficiency. The one that we're going to talk about the most is capacity, because that's the most useful one to work with. The efficiency one, the economic balance one, is a more complex issue and is rarely needed. And you'll understand why later on. The balance point is impacted by a few things, and one of the things that impacts it is the outdoor temperature. I'm sure you all know, so forgive me for going through this, how a heat pump works. You know, it's in wintertime extracting heat from outside and transferring it through a refrigerant to the indoor environment. And because of that, it is subject to the outdoor temperature. All heat pumps are measured at 47 degrees Fahrenheit for their nominal capacity. For example, a 5-ton is a 5-ton at 4 tons. I mean at 47F. 3-ton is a 3-ton at 47F. But as soon as that outdoor temperature goes down, the capacity and the efficiency tend to go down with it. On some equipment, it's a flatter curve, and others it's a steep curve. And we'll get into that in a minute. The other thing that impacts the balance point is the technology. So with heat pumps, we have single stage, they're on and off heat pumps, and 2-stage on and off heat pumps. Now the single stage, it's on at the same capacity all the time. These are very inexpensive. Heat pumps have been around forever. I put my first one in when in the late 1970s. They're still around. They're more sophisticated than they were back then, but it's still full on, full off. The 2-stage heat pumps came along later, and they made a lot of sense because you don't need the full capacity throughout the whole winter season. You only really need it during the winter design conditions. The single stage, 2-stage heat pumps eventually came in competition with variable refrigerant flows, they're referred to as VRFs, or variable refrigerant volumes, VRV. So they're the same thing. They're the same thing. Basically, the heat pump modulates. It's not all on or off. It actually, when it comes on, it kind of starts really low and it ramps up to meet the load condition. It's extremely efficient, quiet, very, very effective technology. And recently, more recently, cold climate heat pumps. That's a new advance in technology. It uses the variable refrigerant flow technology, but it adds to it. It has enhanced technology on board, which allows it to maintain its capacity and its efficiency down to sub-zero temperatures. So if you look at this graph here, you can see the red line starting at 47F. All 3 heat pumps are at the same place. They start at the gate at the same place. As soon as that temperature starts to fall, you can see the standard heat pump in blue. That's your single stage, 2-stage standard type of heat pump. It drops off very dramatically in terms of its capacity. And there is more or less a correlation between capacity and efficiency in that curve. You can see the green line there. It's a lot shallower. It's much better performing at lower temperatures and has a similarly better efficiency as you get down to sub-zero temperatures. But look at the red line. You can see how that's flat until you get to about 5 degrees Fahrenheit, and then it slightly drops off. It's at 100% at 5 degrees Fahrenheit, which is, I think, about -15 Celsius. And when it drops off, it drops off slightly. It doesn't fall off a cliff. So you still have capacity. You can see at -4 Fahrenheit, it's 87%. and even at -13, still 75% of its capacity. And again, efficiency correlates to the capacity in most cases. They don't diverge from each other very much. The balance point is important when you have an auxiliary, or sometimes referred to as backup heat. Whether it's gas or electric, in either one, you need to know the balance point. There are a few exceptions. Like in the lower mainland, for example, it's often the case if you use a cold climate heat pump, you don't need any backup at all, which is really handy when it comes to things like, the stress on the electrical panel, the ability to take on more amps is reduced if you don't need an electric backup. But those are the minority. In most of the regions of the province, you need to have auxiliary heat, backup heat. It could be gas, it could be electric. Either way, it's extremely critical to understand the balance point. And here's a few reasons why. Equipment selection. You can't really choose which equipment you're going to use unless you know the equipment and its balance point relative to the heating demand and cooling demand of the project. You need to know the balance point to understand how much panel room it's going to take up. This is especially an issue in retrofits, but even in new construction, whether it's electric backup or gas backup, may have a very significant impact on the size of the electrical load. For example, if you have a 200 amp service, knowing where your balance point is will let you know whether you have room on that 200 amp service or you have to upgrade to, say, 400 amps. It's also a good way to do cost benefit analysis, because until you know how much of the time your heat pump at what efficiency is doing the work compared to your auxiliary, whether it's gas or electric, until you know that, you can't do any kind of cost benefit analysis. It would be just guessing otherwise. The other thing is, and finally, system optimization. So once you've figured everything out and you have a system running in your house, somebody needs to set a changeover, a switchover time based on the balance point, the outside temperature, or some other kind of algorithm. But you need to set that the point in time where your auxiliary takes over or assists your primary heat pump source. So how do you arrive at the balance point? Well, it's pretty basic. First of all, you do your load calculations, then you select your heat pump technology, find the performance specs of the equipment, you plot that on a graph with your heat loss line, and where that heat loss line and the heat pump capacity curve meet, where they intersect, that's your balance point. So let's just go through this a little bit. So first step, load calculations. Load calculations, first of all, it's required, even though it's not enforced in all jurisdictions, it's required in, from a standard of practice point of view, you really, 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 really need to do proper load calculations using the methodology that you see in front of you here, the F280-12. If you don't do that, no other step matters. Your heat loss calculation is critical. Once you've done that, the next thing is to select the heat pump technology, whether it's single or two-stage, whether it's a variable refrigerant, or whether it's cold climate heat pump. And the reason that matters, if you look on this chart here, there's three types of technology. They all intersect the heat loss line at different points. In other words, each one of these technologies has their own characteristics of when you need to go into auxiliary mode, or even if you need to go into auxiliary mode. Once you've figured out the technology that you want to use, or you want to explore options in all technologies. Either way, the types of heat pumps out there, all types of heat pumps have performance curves or performance data that you can access directly through the manufacturer's literature or through third-party testing like AHRI or NEEP. There's third-party agencies that test equipment for these things. And we have to be careful because every single brand of heat pump is different than another brand. And within brands, different models within those brands have different performance characteristics. So it's important to look at them all. There's no such thing as a universal balance point. They're all different. You can see 4 different types of heat pump performance curves here. They're all different from each other. So once you've done that and you've selected one or a number of them that you want to investigate, you'll have a performance curve like you see the one in front of you. And then what you do is you plot the heat loss on that line. And we'll get into how that works a little later in more detail. But effectively, what that heat loss line and the performance curve line do is give you the intersection at which your balance point exists. So in this case here, it would be at 19F or minus 7.2 Celsius. So let's go through a project. This is a house that has traveled more than I have. It's a house that Natural Resources Canada has taken. It's an actual house in Ontario, but we have modeled this in many different places with many different kinds of modeling. And so one of them, we put this house, it's a 1980s house, before retrofits in Kamloops with these kinds of assemblies. I don't want to get into this too much to save time, but just suffice it to say it's a typical 1980s house. It's leaky and it doesn't have great amount of insulation. We took this house as is. You can see that column there. We did a light upgrade, which meant that we tightened it up a bit, made it a little more airtight. We blew in our 60 in the attic, and we changed the windows to triple pane. And then we did a deep energy upgrade where we got the house even tighter. As you can see here, 1.5 air changes. We still blew in the R60 in the attic, but we upgraded the above grade walls and the foundation walls, and we changed the windows to triple pane. So there you have it. 3 scenarios, as is light upgrade and deep energy upgrade. The heat loss in Kamloops for these 3 scenarios is what you see here, 95,000 as is, 69, almost 70,000 for the light upgrade, and then it drops down to just over 30,000 for the deep energy upgrade. Okay, so now we know what we're dealing with for the house and load calcs. The first thing in Kamloops, we want to know what is the design condition. Well, it happens to be minus 10 degrees Fahrenheit. Okay, so that's the first line. Then we know the heat loss for the as is 95,000 BTUs. And where that design condition and the heat loss intersect, that there's basically just a linear graph down to 65, at which point we don't need any heat. Now let's look at a standard 1 or 2 stage heat pump. This is an actual heat pump curve. You can see that it drops significantly to the point where you have no capacity left over at about 32 degrees or something like that. 0 Celsius. But look what happens if we use a cold climate heat pump, different technology. That capacity means that the capacity difference means that we don't need to change over to auxiliary until we're about minus 14 Fahrenheit. It's a big difference. With the standard heat pump, you can see that purplish, pinkish section there. That's all the time that we need auxiliary heat. And because we need so much of it, we need the full capacity. In this case here, this example, this as is house in somewhere with this kind of climate condition, we would need, there's no choice, you'd have to have gas backup for this. It would be too large of an electrical load in the panel to try to do the backup with electricity. But look what happens if we put a cold climate heat pump in there. We not only move the point in temperature to a much colder outside condition, we need an awful lot less auxiliary. In fact, we only need about 35,000 BTUs out of 95. We don't need the full backup. So this now becomes possible to do this with a bit of an electric strip. You can still use gas as your auxiliary with a cold climate heat pump, but at least it gives you more options. If we do a light upgrade, and the reason I'm showing you this is because any house with a lower load, essentially, whether it's a retrofit or a new house, doesn't matter. The point is the same. The load is now only 69 with that upgrade that we had talked about, that light upgrade. We still need a 5-ton heat pump. It still drops off close to 0 degrees Celsius to the point where we need backup. We still need the full capacity backup with probably gas furnace. And with a cold climate heat pump, this is what happens here. Now we only need 10,000 BTUs. We've reduced our auxiliary requirement quite substantially. It's only 3 kilowatts. And we don't need it until we get to below 0 Fahrenheit, somewhere around -2. If we go to a deep energy building upgrade on the same house, that load goes down to 30,000 BTUs. Now that could be a step 4, step 5 new house, right? With a load like that in a typical cold climate region of BC. In this case here, with using a standard heat pump, we can now go down to 4 tons. It still drops off, but it drops off later. The temperature that we need to switch over goes down, so we can use the heat pump for longer. However, we still need backup. We still need auxiliary heat. On the other hand, if we go to a cold climate heat pump, it actually matches the load. There's no backup required. This is pretty significant consideration because the upgrade cost to go to a cold climate heat pump is not that significant compared to the cost, for example, of upgrading your panel or putting in a new gas furnace as your auxiliary. The cost of that furnace, you need gas lines, you need to vent it through the building, you need to bring in combustion air and everything else associated with it. You might be able to avoid that. I wouldn't always recommend that in especially remote areas where service is not immediate. If you're in a dense area like in Kelowna, for example, Kamloops, Vancouver, of course, Victoria, the Lower Mainland, you can get away without backup if you can design a system to work without it. But if you're somewhere where it's hard to get service, it might be a good idea to have backup, just to have backup, not because you need it. Thermal or economic balance point. Remember, one is about capacity, one is about efficiency. Now, you still have to do your calculations for the capacity, the thermal balance point, to then do the next set of calculations for the economic balance point. And it's not simple because it depends on a lot of things. the cost of the energy and how much time that energy is going to be in primary mode. Your heat pump is doing all the work, in auxiliary mode where your electric strip or gas is doing the work. So it's not simple. It's not a simple set of calculations to make. Economic balance point is all about cost, right? So let's look at this house. We'll put it in Vancouver and look at some cost implications. So for 1 hour of operation, the same house as is in Vancouver, let's just look at that one column, the cost of natural gas. And this will be the same throughout the province with very, very small variations, except perhaps in the north where the energy costs are different. 1 hour of natural gas is $1.24. If you go straight electricity, like baseboard, for example, electric strip, $2.17, almost double. If you get a standard heat pump, its efficiency will be about 200%. It's measured in COP, which means coefficient of performance. All that is the ratio of kilowatts of electricity versus kilowatts out of heat. But if it's easier to consider it in terms of efficiency. So a COP of 1 is 100%. That's your baseline. That's straight ahead electricity. Go to a heat pump, it can work at 200% efficiency. Now your cost for that same hour of heat on that same house is $1.08. It's less than the cost of gas. Keep that in mind. It's a standard heat pump. It's nothing special. You go to your good quality variable speed heat pumps and some of your cold climate heat pumps. Now you're down at 87 cents for that same hour. Relative to the cost of natural gas, it's less expensive. And of course, if you go to the top type of quality heat pumps, or geothermal, for example, now you're down at 72 cents for that same hour. Just to summarize that, 1 hour for that house of heating with natural gas is $1.24 compared to $2.17 for electricity. To match that $1.24 in operating costs, the heat pump's efficiency only has to be a COP of 1.75, or another way to look at it is 175%. That is pretty standard. It's not a special heat pump. This graph here, and don't mind the complexity of the graph. I think the line that you need to see is a heat pump operating at an efficiency of 1.75 is actually below the efficiency of standard heat pump. So that's why I say you really need to focus on the thermal balance point more than the economic balance point. And that's because if you do that, it's extremely likely that the efficiency of the equipment will correlate to the capacity of the equipment, and the efficiency will be above that 1.75 in most cases. So understanding the balance point of heat pumps is critical for choosing which technology and brand of equipment is most suitable for your project. And you think about it, how can you know? How can you know? How can you make any decision about A, which technology, B, which brand, and C, which model of those brands is the one that suits your project? It's most appropriate. Could be about budget, could be about performance, it could be about accessibility. What product line is available in the region that you're working in? Which product line is the one that your mechanical contractor has a relationship with? All these things matter, but you don't know any of that. It's just pure guesswork unless you know the balance point. It also helps you figure out, should my auxiliary be electric strip, or should I put a gas furnace in there, or in the case of radiant heated, gas boiler. It's also the only way that you can actually effectively calculate the costs operating costs, cost benefit, life cycle cost, that kind of stuff, right? If you want to do a thorough cost benefit analysis, you really need to get to know the balance point first. And it's also that system, once it's all installed, needs to know when to switch over to auxiliary. And you don't want it to happen prematurely because you're spending too much time in the alternate fuel, right? You want to have that heat pump work as much as it can to the coldest temperature it can, and then switch over. Simple as that. Calculating the balance point begins with heat loss calculations. Heat loss calculations are critical. They, without load calculations, you can't do the balance point calculation, but you also can't do anything else that well. I mean, if it turns out that you have a system that actually is working well in the house after it's installed without doing the load calculation, that's an extreme coincidence. Use equipment performance specifications to plot the capacity and efficiency at varying outdoor temperatures. Again, all equipment publishes that in one form or another. It could be a graph of performance curve like you see in those graphs that I've showed you. Sometimes they do it as a percentage of capacity. 100% at this temperature, 90% another temperature, 80% another temperature, and so on. Either way, they're all manufacturers publish them, and you can verify those published performance specifications with third-party testing agencies like AHRI or NEEP, NEEP. And finally, the economic balance point is a complex calculation. It really did matter more years ago when the costs of energy between natural gas and electricity were very different. In those days, you should have done your economic balance point calculations, but these days, because of the current conditions, and who knows how long that'll last, but at least today, the way natural gas is costed and electricity is costed, you're really better off to stick to the capacity balance point, the thermal balance point. In, I'd say 90+% of all products, the thermal balance point will also be your economic balance point. In other words, just push that heat pump to the lowest temperature you can, and you'll have achieved the whole exercise of going through a economic balance point. So here's some resources here. Natural Resources Canada has some really good information. It's worth checking out the site. NEEP is the agency I referred to earlier. It has a lot of third-party information about all kinds of heat pumps, cold climate heat pumps particularly. AHRI is a testing agency. They have a directory. You can look it up by type of heat pump. You can look it up by manufacturer, by model. It's a really good resource, and it gives you the tested, third-party tested performance specifications of all kinds of heat pumps. Finally, the Home Performance Stakeholder Council, they have a guide for best practices for installation for existing homes. Worth checking out any of these. And that's it.
Great, thanks so much, Rob. We have had a couple of questions pop up in the chat. Oh, but I wanted to let you know at the beginning when you asked how many people were familiar with load calculations already. We had 2 people.
With balance point?
Or with balance points, yes, sorry.
Yeah, it surprises me considering how important it is. And it's easy when you're in, do what I do, that it's easy to take for granted. Just think that, okay, everybody knows this, but it's not the case. But if I was a builder, homeowner, I would consider sticking my hand out, asking for that balance point calculation, or working with my mechanical contractor or mechanical designer to understand what's the balance point of the equipment that we're considering. I think it's important, because if it doesn't get done, then we're really taking a chance and a risk that we are not optimizing the installation.
Yeah, great. So we do have a few questions in the chat here. I'll just go through them in order here. So sorry, I have some cats. I want to be fed their breakfast. Jumping up here. But Maurice asks, do heat pumps have internal heating coils to provide auxiliary heat when the design temperatures cannot be met?
That's a good question. On the air to water system, some of them do. They'll have a electric strip plate, for example, right? But on the heat pump itself, that's more restricted just to those particular air to water heat pumps. But a heat pump will have connected to it by refrigerant lines and some wiring, an indoor unit. And that's where you find the electric strip. And in a lot of brands, that is something that is, you just snap it in. It's accommodated with the fan coil unit inside the house. Others you have to add to it, but either way, it's very rare for an outdoor unit to have it on board.
Great, thank you. Edwin says, you speak of load calculations. However, there are variables that are hard to pin down, such as infiltration and internal gains. How can we have confidence that loads have been estimated correctly? It feels like giving the same problem to two mechanical designers will result in different estimates for the same building.
Yeah, I mean, that's a fair instinctive perspective. But the fact is this, that the F280 methodology for calculating heat loss and heat gain in residential has been tested. It's been worked out and it's been tested and peer reviewed and tested and so on. And it finally came out in 2012. And since then, it's been field tested, actually tested over and over and over, all across this country. Who knows? Thousands and tens of thousands of times. And it works. The fact is that the physics of what creates heat, where heat is lost, how fast it's lost, how it's lost, what internal gains are, and all that is not actually rocket science. It's actually pretty predictable. The only thing you cannot predict is lifestyle, right? But that is a different story. Once you you calculate the load of the building, you know, it's fair enough, you know, leave windows wide open, doors wide open, and all that kind of stuff. That's lifestyle. You leave all your lights on, and, you know, that kind of stuff. But there is a standard that we can use that will very, very adequately determine what the heat loss is and what the heat gain is for the purposes of designing systems that works extremely well.
Great. And Bruce is curious to know approaches to balance point with mini splits, i.e. baseboard backup.
With mini splits?
Mm-hmm.
I'm sorry, did you say, Jenna? I'm sorry, I didn't hear that last part.
Approaches to balance point with mini splits, i.e. baseboard backup.
Yeah, the difference is that it's a separate, the calculation is the same, right? It's a heat pump. How much heat can it put out at what temperature? And then where you need to switch to an auxiliary heat, then you need to go to, could be baseboards, it could be fireplaces, you know, efficient fireplaces. It could be And another system like your radiators, for example, in Vancouver, that's pretty common. Old houses with old boilers and radiators. You know, you can put in ductless splits in that house and have a new boiler, for example, or an air to water heat pump, back it up with radiators. So it's just a different system. It's not incorporated like it is with a forced air system. It's separate than the indoor unit. So you got a console on the wall, there's a heat pump. Gets to a certain point, it can't keep up. Now your electric baseboard, for example, somewhere it's going to take over.
Yeah, great. I think you already answered this next question, but I'll just read it to you in case you have more to say. How accurate is HOT 2000 for calculating? Oh, sorry, no, you didn't answer this. How accurate is HOT 2000 for calculating heat loss?
Well, HOT 2000 is a different kind of set of calculations. HOT 2000 is there to determine the thermal performance of the building. Really, that's all it's there for. And it has been created to be standardized across the country. So no matter who's using that program, you're not monkeying around with customizing inputs. Otherwise, you don't get a fair comparison to a baseline. And so it's reasonably accurate on the heating side, but not so much on the cooling side. It's way off on the cooling side. But the other thing that's different about it is because it's not there to help design a mechanical system. That's what the other load calculation, F28012, is for. You tend to just do a block load, the whole house. There's one big block, it's called block load. Whereas if you're doing load calculations for the purposes of designing a mechanical system, you're doing room by room. That's the other difference. If you have two happening, which is very often the case, you know, an energy advisor is doing a blower door tests and other things and modeling the house's thermal performance with a block load using HOT 2000. Whatever that outcome is of the total block load of the building, it should be close, like 10% of the heat loss that you come up with from the F28012 calculations. If it's outside of that range, then you know something wasn't input correctly in one or the other of the two sets of calculations. But ignore the cooling load on HOT 2000, it's way off, and Enercan's working on that.
Great, thank you. Eduardo says most heat pump installers size the heat pump by the square foot of the house. He doesn't, but it is the norm in the industry. Any comments?
Yeah, it's sad, but true. It is the norm, and it's I don't know, we're going through a period of time right now where there's a lot of disruption, and most of that is, you know, the climate crisis and government policies to address those, right? And changing in technologies and all that kind of stuff. And in my world, this is a good time to kick the ass of the HVAC industry, because it's just a frontier. There's no standards of practice in the culture of mechanical contractors of good standards of practice, but that's changing. So those who just, you know, rule of thumb it or go by some, you know, square footage calculation won't be able to do that for much longer. Within, I think, probably 3 years, the next set of code changes is coming out, and things that are happening right now with, and in this province, but across the country as well, with jurisdictions with authority, tools are being provided, processes are being put in place to actually create a set of standards and the verification requirements that come with those standards. So if you're not doing good practice now as an HVAC contractor, you will need to have to figure out how to do it within the next few years.
Great. And then another question by Eduardo. He asks, what considerations do you suggest for air quality, specifically CO2, to be maintained below 1000 ppm?
Oh, there's a rabbit hole. Okay, good air quality means you're replacing the air, that closed loop inside the building. You know, you're injecting fresh air from outside, and hopefully you're doing that in a way that recovers the heat of the stale air going out. So energy recovery or heat recovery system, an ERV or an HRV. So that's the first thing. He probably MERV 13 or better filter. So not your 1-inch rock catcher that you get at Home Depot. It should be 4-inch pleated minimum, because you need that surface area for it to be effective. That will take care of a lot of the particulates in the home. And then that's probably enough for most. But if there are respiratory issues, health issues, allergies, that kind of stuff, then a good approach is go to the MERV 15, for example, and put an ultraviolet light into the plenum of the furnace to kill bacteria and other stuff as it passes through. If you have issues, and I don't know if there's anywhere in the province that hasn't had this issue of smoke coming in from wildfires, then the only and most effective way to deal with that is to put an activated carbon filter on the airstream coming into the house. If you wait till it's already in the house and then try to clean it, yeah, that's good for the air coming out of the registers, but you still already have it in the house. The better approach is to filter it on the intake of the HRV or ERV, put an activated carbon filter there.
Great. Sarabjot says, very informative webinar. He's been in the field since 1985, and thanks for refreshing his knowledge and educating some new techniques as well. Greg says, energy advisors are not required to compare the HOT 2000 results with the customer's actual gas and electrical bills. That's too bad. Not sure if you have a comment there or just agree. Edwin asks, what are the dangers of oversizing a heat pump? So Sarabjot suggested money wastage and the system will not work efficiently. Anything else to add there?
Yeah, I mean, you can oversize it a little bit, but not much. I mean, you know, for example, if your heat loss is, say, 33,000 BTUs, and the heat pump that you're thinking about has a capacity of 3 tons, 36,000 BTUs at the design condition, well, you're oversizing it. But you're just going to the next size up, really. It's not that big of a deal with the variable refrigerant flows. It's oversizing it substantially that matters a lot with any kind of heat pump, because it's about the airflow, really, because there's a finicky things going on with airflow and heat pumps, and that's you're taking a refrigerant and you're constantly changing states. You know, you're going from a vapor to a liquid, a hot vapor to a cool vapor to a liquid, and so on. And you're compressing it, and so the airflow relationship with the airflow to the properly performing cycle of the refrigerant has to match up. And if you oversize that, that's when you have an issue, freezing refrigerant coils and that kind of stuff, or it's going off on high limit, you know, you've exceeded the pressure it can take and that kind of stuff.
And then just a follow-up question there, Bruce asks, does cycling on and off affect the lubrication of the pump and therefore lifespan?
It affects, yeah, that's a good question. It affects everything. It does affect that. It does affect the lubricant and the refrigerant, and therefore everything that it's touching, which primarily the compressor. But it's just like anything, you know, that energy it takes to start something up and then switch it off, start it up, switch it off. You're creating stress on all kinds of components of the system. So it's going to shorten its lifestyle cycle. It's going to cost more to operate, have more maintenance and repair issues, and it's not going to be comfortable. You need your system to cruise. That's the the most ideal situation is when the system is cruising to keep you comfortable, as opposed to off and on and off and on. And with off and on, you're not going to get consistent, even temperatures. It's going to be uncomfortable as well.
Great. Eduardo says heating degree days and cooling degree days are better approximations for calculating the heat load. Where does this come in your approach?
Say that again.
Heating degree days and cooling degree days are better approximations for calculating the heat load. And where does this come in your approach?
Well, they're part of the calculation, right? If you do a proper load calculation, those kinds of numbers, that data is embedded into the program. So it's not a better way. It is the way that load calculations are part of the way. I mean, there's other data that's taken into consideration as well on all your inputs and everything else. But the heating degree days, bin hours, there's all kinds of data that you use to do proper load calculation.
Great. And we're going back up to a question Bruce asked earlier. Sorry, he provided a clarification, but that was, I'm trying to find the original question here. That was when Bruce was asking about the approaches to balance point with mini splits. And then he just clarifies. The question was how to set up a system so the auxiliary heat will kick in at the right time with a minimum of user manual input. Just set the set point at slightly lower and special tricks or products.
That's complicated because it's about controls. It's about control. So you have on the one hand, either a remote control or a hardwired control on the wall, controlling your mini split. Yeah, your backup, say it's electric baseboard, for example, is another independent separate control on the wall, right? So the simple way to do that is to have the set point of your baseboards so that when your heat pump is not keeping up, it's losing temperature, right? It just can't do it, it's running out of gas. And what happens, the room temperature will get below a certain point, then your baseboards could kick in. That's one way to do it. Another way to do it, and a better way to do it, is to connect them both to an outdoor sensor, so that basically the sensor is controlling when the backup comes on. But that's not simple. You need a bit of relay logic and other control modules to make that happen. So it's about the controlling aspect of the two and how they're integrated, how they talk to each other. And there's no simple answer to that. There's many different controls. It takes a good contractor, and it's many that would have to create the control logic, either with off-the-shelf control modules from different manufacturers, or create it with their own relays. Either way, it's a controls thing. But it's a good question, because it's something that, especially in a retrofit situation, that gets overlooked quite a bit.
Okay, great. We just have a few more minutes here, so I'm just going to take these last 3 questions. Eduardo was just clarifying when he was asking about CO2, when asking about what considerations do you suggest for air quality, specifically CO2. He was referring to CO2 that is in the house and needs to be reduced, and then notes that CO2 cannot be filtered.
Well, CO2 can be mitigated if you change the saturation of content of CO2 with oxygen, right? more oxygen. And so, when CO2 is not typically an issue in residential. It can be like in commercial Part 3 buildings, depending on the size of the gathering and so on, there could be a need and requirement to manage the CO2, and in which case you'd have CO2 sensors, and those sensors would bring on other HVAC equipment to deal with it, like bringing fresh air into the space. But in residential, that's rarely an issue. But if you're concerned about it, I would treat it the same way as a Part 3, which is have a CO2 sensor, and then have that sensor actually engage a fan with HRV or something to saturate the unit with oxygen or pressure, so bring more pressure into the space.
Great, thank you. Maurice asks, what is the best resource for finding the design temperatures for different locations?
BCBC, the building code. Building code has a section 93 something, 93. There's a table in 935, I think it is, but could be wrong, 93 something. But yeah, it's got every, well, not everyone. It has all the regions, municipalities, design conditions, winter and summer, among other things, wind, snow loads, everything else. And yeah, so that's pretty good. What I would recommend though, because the data they use is kind of historical over a large period of time, I would, whatever you consider for your design condition, add something to it. Like in Vancouver, for example, we've had a few summers in a row, especially that heat dome, where our temperatures were way above averages, way above the design conditions that you find in the code. So as a rule, we designed for recent averages. So it's a little higher than what you'll find in the code in the summer, and a little colder by a couple of degrees Celsius in the winter.
Perfect. Just recognizing that it's 9 a.m. I just want to launch this feedback poll. We've been getting some really great feedback from you guys just in terms of how you've enjoyed the webinars, as well as ideas for future topics. And we really, really do appreciate all this feedback and do take it into consideration when designing future training. But Rob, there's one more question here. Are there CCHP available that use refrigerants that don't contribute to climate change?
There's not yet. There's one product out there, sand, and it uses CO2 instead of R410. R410 is still the predominant refrigerant for heat pumps. That is changing. I mean, it's the U.S. is the holdout. I mean, if you're into conspiracy theories, it's big players in the industry, chemical industry, that are trying to keep it the way it is. Who knows? All I know is that there are other refrigerants that have been tested and that are effective, but they're just not in the market yet. I'm not sure when they will be, but for now, there's only the send and heat pump, which has CO2 as its refrigerant instead of R410.
And I'm going to squeeze one more question in because we have one last one here. Are there any load calculation computer programs that you recommend?
Yeah, there's a couple. The RightSoft is a robust software that uses F28012, RightSoft. Another one is LoopCAD. It's an AutoCAD-based program. LoopCAD uses F28012. But probably the most successful one, most inexpensive one, but perfectly fine for straight ahead load calculations, is from TECA. That's the industry organization for mechanical contractors in BC. TECA is their acronym, Thermal Energy Comfort Association. And they have a very inexpensive program. They support it well, and it doesn't have a high learning curve. And I would recommend that for anybody that's not into full-on designing systems. It's the ideal one for a load calculation that doesn't require you to design a complex mechanical system for a Part 9 building. The other ones are heavier, more expensive, and higher learning curves. But they're for somebody like us, that's worth it, because that's what we do every day.
Okay, wonderful. And we have a lot of thank yous in the chat, and a big thank you from me as well, Rob. That was great, really informative. Really appreciate it. And thanks to everyone on the call for joining us today and for providing your feedback, and enjoy the rest of your day.
Thanks, everybody.